The next gas law we're going to talk about is Avogadro's law. And Avogadro's law talks about or compares volume and amount of gas, which is going to be in moles. And the volume and the amount of gas has a direct relationship. So just like what we saw in Charles' law with volume and temperature, moles of a gas and volume are directly related. So in our graph here, we have mass. So it's not moles, but we know that we can go from moles to mass if we use the molar mass of the gas. So we have mass on our x-axis, volume on our y, and we can see as the mass is increasing, the volume is increasing as well. So again, there's that direct relationship. And so if everything else is held constant, then we can set volume in moles in this equation down here. So it looks very similar to Charles' law because it has that direct relationship. So we have V1 over N1 equal to V2 over N2. So for this, for an example for this gas law, if you blow up a balloon, okay, so if you start with a balloon and it's flat because there's no air in it, but when you begin to blow air into it, you're putting a gas in there, right? So the air is a gas. And the more gas that you put into the balloon, the larger it gets. So the volume is increasing. And then if you let that air out of the balloon, so the amount of gas is coming out of the balloon, your volume will begin to decrease. So that's kind of that relationship that we see with Avogadro's law. Okay, so now using the equation, we're going to look at this equation. With Avogadro's law, it's a little more tricky because it's dealing with moles, and there's a couple of different ways to ask a question using Avogadro's law. So this isn't really possible with Boyle's or Charles. So really Avogadro's is really the only one that's tricky like this. So because we have moles of a gas, we can also use stoichiometry in this. So I'm going to show you how to do that. So again, reading the question and seeing that the only two things that it's talking about is moles of the gas and volume of the gas helps us to know that we need to use Avogadro's law to solve this problem. Okay. So I'm just going to rewrite these like I've been doing. So V1 equal to, we'll see here in a second, N1, V2, and then N2. Okay. So as we read the gas, it says a sample of gas contains 2.4 moles of sulfur dioxide and 1.2 moles of oxygen, and it occupies a volume of 17.9 liters. So it's giving us, well, first V1, right? 17.9 liters. Okay. But then it's given us moles, but it's giving us moles for the reactants, right? Before the reaction takes place. So our initial moles is 2.4 plus 1.2. So it's both of those. That's what we initially have. So we have a total of 3.6 moles to begin. Okay, so then it says the following reaction takes place. Calculate the volume of the sample after the reaction takes place. Okay, so we want to calculate the volume, V2, but we need N2 to be able to do that. So we can use stoichiometry and go from one of the reactants, it doesn't matter which. We can go from SO2 to SO3, or we can go from O2 to SO3. So it doesn't matter. We just have to use that mole to mole ratio to figure out how many moles of product were produced. Okay, so I'm just going to pick moles of SO2, which are 2.4 moles SO2. And the ratio is 2 moles of SO2 to 2 moles SO3. Okay, moles of SO2 cancel, and then I get 2.4 moles SO3. Okay, now if you were to do that with oxygen, you'd get the exact same thing. So 1.2 moles of oxygen. Then we use the ratio. It's 1 mole of oxygen. Whoops. 1 mole of oxygen to 2 moles of SO3, and 2 times 1.2 is equal to 2.4. So it didn't matter which one we used, you're still going to get the same amount of moles in the product using stoichiometry. So now we can put that in and say we have 2.4 moles. Oops. This thing keeps popping up here. 2.4 moles for a product. So now we have everything we need to solve for the V2. So I'm going to switch over here real quick. Okay, so again, if you want to rearrange the equation, you can. If you don't, that's totally fine. You can just solve for x. But if you'd like to rearrange the equation, then I'll just show you how to do that real quick. So we want V2 by itself. So we have to move N2, so it's being divided over here. So I'm going to multiply it up here. And that gives me V2 is equal to V1 times N2, whoops, divided by N1. Okay, so I plug those numbers in, and I have 17.9 times 2.4 moles. I forgot my units here. I'm going to squeeze this one in here. Is it liters? 17.9 liters, 2.4 moles, divided by 3.6 moles. So your moles are going to cancel. That leaves you with liters. And that gives us 11.9 liters. So we saw that we went from 3.6 moles to 2.4 moles. So our moles decreased, which means that our volume is going to decrease, which it did. And we went from 17.9 liters to 11.9 liters. Another kind of tricky way to ask this question, sometimes you'll see it'll say the sample of gas contains this many moles. How many more moles do I need to get to this volume? So instead of just stating N2, the answer, you would have to take N2 minus N1 to state the additional moles. So that's another kind of tricky way that this question is asked. So it's not just straightforward like the others are. Okay. We can put Boyle's law and Charles' law together, and we get the combined gas law. So we have P1V1 over T1. So just to point this out real quick. Okay, so here's Boyle's law, right? And then V1 over T1, V2 over T2, that's Charles' law. So we're just basically squishing these two laws together to form the combined gas law. So, whoops. When we read these word problems, it's going to mention pressure, volume, and temperature. So all three are going to be in the word problem. So this one says, if I initially have a gas at a pressure of 12 atm, a volume of 23 liters, and a temperature of 200 Kelvin, and then I raise the pressure to 14 atm, increase the temperature to 300 Kelvin, what is the new volume? So we're solving for V2, okay? So again, I'm just going to put these over here. P1, V1, T1, P2, V2, T2. Okay, we know we're solving for V2, right? It says, what is the new volume? So we're solving for V2. So let's put in the rest of these. We have initial pressure of 12 atm. Okay, V1 is 23 liters. And a temperature of 200 Kelvin. So that's our initial set of conditions, and then we raise the temperature, we raise the pressure to 14 atm. I'm not sure what happened to that P. 14 atm. And the temperature to 300 Kelvin. Okay, so we are going to plug these numbers in, and we are good to go. So you need to make sure you match, all the units. So we have atm, so that's good. And we have Kelvin and Kelvin, and our answer will be in liters. Okay, so the units are all good to go. So let me switch over here. Again, we're solving for P2. So I have P1, V1 over T1 equal to P2, V2 over T2. So I want V2 all by itself. So I'm going to have to move T2 over here, and we're going to multiply because it's being divided there. And then here we're going to move P2 down here because it's being multiplied, so now we're going to divide it. So V2 is equal to P1, V1 times T2 divided by T1 times P2. Okay, so now we can plug in our numbers. We have 12 atm times 23 liters times 300 Kelvin divided by 200 Kelvin times 14 atm. Okay, so we find our V2 is going to be 29.6 liters. 29.6 liters. Okay, now we can put the Boyle's law, Charles' law, and Avogadro's law all together into the ideal gas law. So the ideal gas law, the only thing it's missing with those three gas laws is a constant, and so that we use R, which is called the ideal gas constant, and it is 0.08206 liters atm over moles Kelvin. So you do need to know that number. Okay, but again, you should be doing so many of these problems that you just memorize it because you've done so many. So don't just sit there and memorize this number, just do lots of problems. Okay, so we can put these together now. We have P times V, so that's our Boyle's law because they're inversely related. And then we have V equal to N, right? That's our Avogadro's law. And then we have V equal to T, so that one looks a little funny, sorry. That's our Charles law. So all three laws right there in the ideal gas equation, along with our gas constant. So this one's a little bit different than what we've been seeing. So it's called an equation of state. So here's down here, equation of state. And what that means is it doesn't matter what the conditions of the gas were previously or what the conditions of the gas will be. It only matters what the conditions of the gas are at this moment, okay? So, what we've seen in the previous gas laws is, here's our initial set of conditions. Now, here's our new set of conditions, okay? It's not going to be like that with the ideal gas law. It's going to say, here's my pressure, here's my volume, here's my temperature, now how many moles are there, okay? Something like that. So it's going to give you the conditions at that moment. Another thing is this equation can only be used for an ideal gas, and there are two assumptions that we make for an ideal gas. And number one is We assume that they do not have volume, and what we're talking about is the molecules themselves. So we're not talking about the volume of the container. So we know that the gas takes on the volume of the container, but we're assuming that they do not have, the molecules themselves do not have volume. And then number 2, we're assuming that the molecules do not interact with each other. So those are the 2 things that make an ideal gas. So you don't have to worry about wondering if the gas that you're working with in the problem is ideal or not. It will be, but just know that there is a difference between an ideal gas and a real gas, okay? So you will just be working with the ideal gases. Okay, a lot of times your problems will say it has STP conditions, and STP stands for standard temperature and pressure. Whoops. So we've already seen standard pressure. That was at the very beginning of this chapter. Okay, standard temperature and pressure. So we saw that standard pressure was 1 atm, and standard temperature we haven't talked about, but it is 0 degrees Celsius or 273 Kelvin. Okay, so if it says it has STP conditions, it's actually giving you the temperature and the pressure that you need to solve for the problem. Also, another thing about STP conditions is at STP conditions, 1 mole of an ideal gas is equal to 22.4 liters. So this is a nice little conversion factor that you can use, but only if you have STP conditions. Okay, so I'll use this here in a little bit just to give you an example. But if you totally forget standard molar volume, it is not a big deal, because don't forget STP, because that will tell you have 1 atm and 0 degrees Celsius, and you can just plug that into your ideal gas equation. Okay, so let's try a problem. Okay, so this one says we have calcium carbonate, and it decomposes when heating to calcium oxide, yes, but carbon dioxide. That's our gas. So that's what we're going to be focusing on, because the ideal gas law can only be used for a gas. So a sample of calcium carbonate is decomposed, and the carbon dioxide is collected in a 250 ml flask. So for that whole thing, we get the volume. Okay, the volume is 250 mils. It says after decomposition is complete, the gas has a pressure of 1.3 atm. So there's our pressure, and a temperature of 31 degrees Celsius. There's our temperature. Okay. So how many moles of CO2 were generated? So again, you can see we're not going from an initial set of conditions to our new conditions. It's just what everything is right now. So we're going to be solving for moles. So we're going to solve for N, so that means we have to move R and T. Okay. So we have N equal to PV over RT if we rearrange the equation. Okay, so they've given us P, it's 1.3 atm. They've given us V, it's 250 mils. They've given us, they haven't given us N. We know that's what we're solving for. And R is always the same. And then T is 31 degrees Celsius, but we're going to change that to Kelvin because we always need to change to Kelvin in this chapter. So we're getting 304 Kelvin. Okay. So we are not quite there yet. One more thing I need to point out, which I'm realizing I just forgot. Let me go back real quick. Whoops. Okay. So the R value has units of liters times ATM divided by moles times Kelvin. So all the units that are in the ideal gas equation have to match R. Okay, so pressure has to be in ATM. Volume has to be in liters. Moles has to be in moles, and then temperature has to be in Kelvin. Okay, if it's not like that, then it's not going to cancel out. Okay, sorry. Totally forgot to say that. Okay, so we are going to plug our numbers in. Okay, so we have 250 mils, okay, but that goes to 0.25 liters, okay, 0.25 liters when we divide it by 1,000. Okay, so now we're going to plug that in. I'm going to switch over here because I'm out of room. So we want moles is equal to PV divided by RT. Okay, so our pressure is 1.3 atm. And our volume, it was 250 mils, but we need it in liters, so we're going to put it, divide by 1,000, we get 0.25 liters. Okay, R is always 0.08206 liters, atm, moles, Kelvin, times temperature, and so it's 31 degrees Celsius, but we add 273, so it's 304 Kelvin. And you'll see, okay, atm cancels, liters cancels, Kelvin cancels, and now I'm left with, moles. Okay, that's what we want. Okay, so N is equal to 0.013 moles of carbon dioxide. And that's it.